emission in the city. Okay, so before I go into detail of what are the general equation or how can we do the emission inventory, we should talk about some of the general status of the emission in the developing country. So these 4 points are usually the general features of the emission in developing countries. The first one, mobile source, are the major source that usually contribute about 60 to 80% of the urban air pollution. This is because first, we have the fast increasing of vehicle fleet and also the slow increasing of the road coverage. This one will lead to the traffic jam. And then when we have traffic jam, the vehicle on road didn't have good combustion or complete combustion conditions, so that the emission gonna be more. And with the time spending more on the street, then the emission gonna be much more from the traffic. The second one, also important, that we have very long life of vehicles that we use in the city, right? In developing countries, most of the country don't have the regulation to remove some of the old fleet out of the in-use vehicles fleet in the city. And then if you look at in terms of the emission, that the old vehicle, for example, vehicle that registered 20 years ago compared to the maybe the current engine that are recently manufactured, the emission can be maybe 10 times or more than 10 times different, meaning that maybe 10 to 20 new vehicle gonna be emit maybe lower than one old vehicle and so on. And with those kind of high composition of old vehicle on the road, those will also introduce very high emission in the street of the developing countries. And then last one, with the intrusion rate of the slow intrusion rate of European standard, maybe the engine standard in terms of both engine standard and the fuel standard, that's gonna be making the movement to the lower pollution from the transportation slower. So that's gonna be the general information about emission from mobile source. For the cooking source, this one also important for developing countries, especially that the country or maybe in the rural area that they still use solid fuel for the cooking. When we are talking about solid fuel, this one mean like using fuel wood, use crop residue, use dung, or use coal or something like that. Then the next one gonna be open burning. This open burning can be the forest fire, can be solid waste open burning on the backyard because of maybe not coverage of the waste management system or something like that. So that when you have solid waste, you want to get rid of it, and then you don't know how to get rid of it because there is no waste management in the area. So maybe you need to burn those kind of waste on the backyard. And also crop residue open burning, like after harvesting, then the fastest way and then maybe the cheapest way also to get rid of those kind of crop gonna be open burning. And then last one gonna be the small and medium industry. So this one put as small and medium industry because when we're talking about the technology issue of the small medium industry compared to the big size industry, those big size industry, maybe most of them gonna be international corporate. Then those international corporate, they have a lot of money to invest, and most of the time they also need to trade among different countries. So they may already acquire some of the international environmental standard, so that they need to implement some of the control device in order to reduce the emission from their factory, which is not the same of the case of the small and medium industry, that they're gonna have very limited budget. So that if they have limited budget, most of the budget they're gonna provide on the maybe improving the process or something like that, and then maybe not enough budget gonna put on the emission control. So this one gonna be the general features of the emission in the developing country, and these 4 points or sources gonna be the major source in the developing countries. Okay, so the use of emission inventory for National Air Quality Action Plan. Well, the emission inventory can be used to identify the key source of the pollution, right? Where the pollution are coming from. It can be used to identify the pollutant of concern. For example, what type of pollution, how much of emission that come from different sources, and so on. And it can be used in order to tell where the pollution are generating, right? Which part of the city, which part of the study area, and then what should be the emission trend in the future if we look in terms of the data in terms of the time series. And then if there is no control option or policy option implement, then what will be the future emission? And then particularly if you focus on the policy and planning, emission inventory can be used to for the preparation and the review of the strategy and regulation. It can be used also to evaluate the emission trend, as we already discussed. It can be used to review the impact of the new source of pollution. For example, the source that not exist in the area, and then you don't know when the source gonna be becoming available, maybe next year, something like that, and then how much emission gonna be coming. So we can use also emission inventory, calculate the source that is not exist yet, and then estimate what will be the source from the new the emission from the new source, and then maybe put into the control option and so on. Next, we can use also in the air quality model in order to determine the ambient concentration. We use emission inventory to check or to meet the national or international reporting requirement. This one in particular for some pollutant, for example, the greenhouse gas, that we have some international commitment, or like, for example, POPs, persistent organic pollutant, that we need to report to the UN, right? And then last one, to provide some of the public information and then raise the awareness of the people, which is one of the important information of the emission inventory. People should know that what are the major sources of the emission in each country or in each location. So if I put the emission inventory in terms of the air quality management with different components, it can be linked and also show the interaction with different components like this. The one in the red here is the emission inventory. And you can see that the different type of emission inventory that we can use. For example, we can have the spatial distribution of the emission in different locations, or we can have the amount of the emission by different sector and so on. We, as discussed, we can use emission inventory to put into the air quality modeling. And this air quality modeling require emission inventory and meteorological data as the required input in order to produce the concentration. And then after it produces the concentration, it can be used to link with the impact, can be health impact, can be environmental impact, and so on. And then emission inventory itself can be used to identify or help to frame the air quality management, right? If you know that what are the major sources, then air quality management can be done in order to control the major source. And also, if based on air quality management, you identify some of the policy, like you need to stop open burning. And then after you identify those kind of policy, you want to know what will be the impact on the emission and the concentration. Then you revise the emission inventory, remove open burning from the emission inventory, and then put that new emission inventory to air quality modeling. You will get a new concentration based on the policy that you apply in. Okay? And then to put into the complete picture, then you have another tool, the air quality monitoring. This air quality monitoring can also put the information into the impact assessment and also give information about whether we should have more strengthened air quality management in the city or not. Okay, talking about the source category that we usually classify for the emission inventory, there are three types of source. The first one, so the first two going to be stationary source, and then the third one going to be mobile source. For the first one, stationary point source, or I will call it point source in short, and then the second one going to be the stationary non-point source, or I can call the area source. And then third one going to be mobile source, as we discussed. The stationary point source going to be non-moving fixed site emitter. The example of this one going to be the industrial combustion process, any stack of the factory or the emission that coming from manufacturing process. Okay, this one is the first one, the point source. In general, it should be the source that you can pinpoint where is the location of the emission. The second one gonna be area source. So this one consider that the emission may be coming from different point source, multiple point source in the same location. For example, like if you have industrial estate, you can consider industrial estate as different point source, maybe 10 point source in the location, or you can combine the whole industrial estate as the area source, as one area source, or something that you could not pinpoint where the pollution of the stack, like forest fire or crop residual open area, that usually the burning is happen for the whole field of rice or something like that. And then last one gonna be the mobile source. This mobile source include the emission from the vehicles, from the engine or the equipment that emit air pollution. It can be moved or it cannot be moved, depend on the subtype. And for this subtype, they usually categorize into on-road and non-road. So as the name say, the on-road gonna be the vehicle that usually, or the engine that usually use on-road. And then for the non-road, gonna be any machinery that don't use on-road. For example, used for the construction, used in the agricultural area, or used for non-road transport or recreation. And also make sure that the time that you identify whether on-road or non-road, like one source, either on-road or non-road, need to be consistent for all of the study area that you apply to. For example, the bus that used in the airport, right? So in that case, if you already classify those bus as the on-road, then you don't need to count it as the non-road again. But in that case, you can see that the bus that used in the airport, sometimes in some emission inventory, people classify as on-road. In some emission inventory, people classify as non-road. So this type of thing, I think you need to be careful when you develop emission inventory and also compare emission inventory to other studies. Okay, so talking about the limitation of the emission inventory, meaning that what information that the emission inventory cannot tell you. Okay, so the first one, when we're talking about pollution, air pollution, we have primary and secondary pollutant. Primary pollutant are the pollutant that directly emit from the source. Secondary pollutant is the pollutant that don't have source of emission. It forms in the atmosphere. For example, if you look at this photo, you can see that there are different sources that emit primary pollutant in terms of particulate matter, NO, CO, SO2, and so on. So this pollutant considered as primary pollutant because it emits directly from the source. There are another type of pollutant called secondary pollutant that develop in the atmosphere. For example, sulfate, nitrate, also particulate matters that may be coming from sulfur dioxide and then change, pass to some process in the atmosphere and then become sulfate particles. So those sulfate particles considered as the secondary pollutant. In this case, when we're talking about emission inventory can be account for only primary pollutant, and it cannot be account for the secondary pollutant. Okay, so that's first limitation of the emission inventory. The second one, the source are limited to the defined study area. For example, this is the Bangkok map, and then I put this boundary as the boundary of different districts in Bangkok. Bangkok have about 50 districts. So if I want to do emission inventory of this district, the red color one, called Wang Thong Lang district, then only the source in Wang Thong Lang district gonna be accounted in my inventory. For example, if there are like some of the factory in this location outside of Wang Thong Lang district, the emission of this factory can be also contribute to the district that I'm interested. Anyway, because of the right now we are talking about emission inventory development, those kind of the factory outside of the study area will not be accounted in my emission inventory. Okay, meaning that the emission inventory cannot include the emission outside of my study area. And then the third one, source need to be known for the emission inventory. For example, this one, we don't know when it can have some fire at the house, like accident or something like that. Or we don't know where the gas going to be leaking from the pipe, so on. So in this case, we could not account those kind of information into the emission inventory, meaning that emission inventory cannot identify the emission from the accidental release or the source that you don't know that it exists in your study area. Okay, so these are the limitations, and it's very important that you understand this kind of the concept of the emission inventory. Okay, for the pollutant from different sources, this one is also the same. I think yesterday you have a lot of this information already. Emission inventory can do for all of the pollutant, particulate matter or gas. In terms of particulate matter, we can do emission inventory in terms of maybe PM10, PM2.5, and different size of particulate matters. For the gas pollution, we can also do emission inventory for different gas like CO, NOx, SO2, VOC, and so on. But remember from the last slide, only primary pollutant can be included in the emission inventory. So for the gas pollutant, secondary gas pollutant cannot be included in the emission inventory. That's why usually you cannot see emission inventory of ozone, right? Because ozone is the secondary pollutant and we could not find the source. So we don't know how to calculate the emission of ozone. Okay, and then this one to maybe give you the information that when we do emission inventory, we also do for anthropogenic source, and we can also do for natural sources. And then for this presentation, I will focus on only the emission inventory development for anthropogenic source, which is going to be referred to the point source, mobile source, and the area source as we discussed in the previous slide. Okay, talking about approach and tiers of the conventional emission inventory, there's two types of emission inventory that we use in order to develop. We call the approach that we use in order to develop the emission inventory. The first one is the bottom-up approach, so starting from the bottom until going up. So this one we will collect very specific information of the activity data, and then I will talk about this later. What are the required information that we need in order to develop the emission inventory? But in general, bottom-up gonna be if you want to do bottom-up approach, we need to collect a very specific, small detailed information of the activity data of individual sources, process, activity, and everything, and also including the emission factors. Top-down, on the other hand, is on the opposite side. Top-down meaning that we can develop the emission inventory based on the national level or regional scale level, which is going to be the data not going to be as detailed as the bottom-up approach. So I will talk about tier of the emission inventory later. But when we're talking about bottom up, because this one we're talking about more detailed data that we need to collect, that we need to use to calculate the emission factor, then the data gonna have higher tier. We have three tiers when we consider about emission inventory development. Tier number 3 gonna be highest, and also the data gonna have highest quality. Tier 1 gonna be the lowest, and the data not gonna be as detailed as tier 3. So for the bottom up, the quality of the data that we will get gonna be higher tier data. For the top down, because we use not detailed data, usually going to be the national scale data or regional scale data or something like that. So the level of the tier that we will get going to be lower tier data. Usually, if you develop the emission inventory for the city or the country or something like that, or for your study area, the combination of both bottom-up and top-down approach gonna be used. Some of the sources that you know more information about that sources, you're gonna use bottom-up. Some sources that you don't have information or maybe not as important in your study area, you may start with the top-down approach to reduce the cost of the emission inventory development. Okay, so to go more into detail about the top-down and bottom-up approach, this slide shows the comparison between top-down on the left and then bottom-up on the right in terms of the methodology, the uses, the advantage and disadvantage. When we're talking about top-down, so right now I'm talking about top-down, which is not detailed. We usually start with the emission factor and activity data on the high level. For example, I can get the national, if you want to calculate emission from the transportation sector in Thailand, then maybe I go to Department of Energy or maybe Ministry of Energy in Thailand, and then look for what are the amount of energy used in transportation sector in Thailand. And then maybe how many petajoule per year, and then I multiply that information with the emission factor. So I will get the information of how much emission that coming from the transportation sector in Thailand. And if I would like to scale down also this information into maybe the city of Bangkok, then I can use some other information. For example, population in Bangkok over the ratio of population in Bangkok over the ratio of population of Thailand, and then multiply with the total emission that I calculate for the national level to become maybe the emission in Bangkok, something like that. So you can use that, you can see that this approach usually we're going to be used when the local data is not available, meaning that I don't know what is the fuel consumption in Bangkok in transportation sector, so I don't have those kind of information, or I don't have emission factor that develop in Bangkok for particular type of vehicle and so on. And also whenever the cost of collect the data is too high, then if we look in terms of the advantage of this approach, the advantage is require minimum resource, right? You can go collect some of the key information, and then you can use those key information to develop emission inventory. The disadvantage is it will be provide you low accuracy and with the high uncertainty. Okay, and then on the right hand side, you can see the bottom-up approach. The bottom-up approach, as we discussed in the earlier slide, you can see that we're going to use very source-specific information. For example, I use the same example. I would like to estimate the emission of from the transportation sector in Bangkok City. Then I need to collect how many cars are on the street. And those number, how many percent are bus, how many percent are truck, how many percent are passenger car. Out of those passenger car, maybe 10,000 passenger car, what are the ages, what are the engine standard, and so on. And then I need to multiply with appropriate emission factor that's going to be detailed in terms of the what technology, what are ages, something like that, what are the fuel type, and so on. So I multiply emission factor with the activity data, the number of vehicle, and also maybe kilometer that each type of vehicle travel per year. So with that information, I combine one piece of information with another piece of information, and then put them together to be the total emission of traffic in Bangkok. So you can see that there are a lot of process that need to be done in order to collect the information to develop the bottom-up approach. Usually, that's why the bottom-up approach gonna be used whenever the source specific information and also the emission data on that particular of the specific information are available. And also the end use of the data of the emission inventory is justify the high cost of the data collection, right? Because you need to spend a lot of time and also resources in order to collect those kind of information. Usually we're going to use this, the detailed bottom-up emission inventory when we want to develop some of the policy and so on. And the top-down approach we usually use to quickly assess what are the major sources of the emission in some location. The advantage of the bottom-up going to be produce more accurate emission estimate, and this advantage going to be require more time, resources to collect the information. Okay, so this is the activities that we need to conduct in order to prepare the emission inventory. The first one, you need to identify the emission inventory manager and the emission inventory compiler. Maybe one person or a group of people, I think that doesn't matter, but these two group of people need to be identified. The emission manager gonna be the one that look at the overall activity of the process, including looking for the source of the information that's gonna be used to develop the emission inventory. And after the emission inventory is developed, what will be the incorporate of this emission inventory into the process of the Clean Air Action Plan. So this is gonna be the inventory manager. The inventory compiler gonna be the one who collect the data based on the identified data provider, compile the raw data in terms of the activity data, emission factor, estimate the emission. Okay, so those gonna be the two key sources: the emission manager and emission compiler. After that, you need to identify the key air pollution issue that you want to use emission inventory in order to answer the question, right? So if you want to tackle PM2.5 problems or particulate matter problems in the city, then this can be one of the key air pollution issue that you want to tackle. Then for the next step, from that particular issue, what are the major pollutants? In this case, going to be particulate matter, both primary and maybe the secondary particulate matter. And as we discussed earlier, secondary particulate matter cannot be identified by the emission inventory, but we can use other pollutants that are the precursor for secondary particulate matter and include those kind of precursor in our emission inventory. And then we also need to select the sources that contribute those kind of the emission of pollutant. And then next, we need to select the inventory domain. So what will be your study area, what will be your base year, and so on. And then the next step gonna be the selection of the temporal resolution, right? What should be the time scale of this emission inventory, whether it's gonna be hourly emission, whether it's gonna be monthly emission, or whether it's gonna be annual emission. It's gonna be depend on how will you use this kind of the emission inventory. And then last one gonna be you need to decide how to report this document of the emission inventory. It can be maybe the document that submit to some of the organization, or maybe you need to put this kind of information on the website, or maybe you need to disseminate this kind of information to the public and so on. So this is the information that I explained in the previous slide that gonna be relating to the activity when we prepare the emission inventory. Okay, now we're gonna talk about some, there are gonna be three basic formula for the emission inventory development method. The first one gonna be the most important emission inventory equation. Most of the emission inventory gonna be developed based on this simple equation, and then we keep adding component into this equation in order to generate more complicated emission inventory that incorporate more factors. But the basic formula is the emission or emission inventory gonna be equal to emission factors multiplied with activity data. Emission factor in this case gonna be the rate of emission that released from the source per activity unit. For example, can be kilogram of sulfur dioxide that emit per ton of the coal burn. And then the activity data gonna be the amount of the activity per time period of the emission inventory. For example, can be the amount of coal burn per year, right? And then you can see that these two information need to be in the same scale or in the same unit, correspond unit. For example, if your emission factor are in terms of kilogram of sulfur dioxide per ton of coal burn, then the activity data that you collect, you need to collect in terms of the amount of coal burn per year. And then when you multiply these two information together, the emission gonna be come out in terms of kilogram of sulfur dioxide per year, right? Which gonna be the same of kilogram CO2 per kilometer traveled by car, which need to be multiplied with the activity data of total distance travel in terms of the kilometer per year. The second formula gonna be based on the material balance. This method is normally used with pollutant that you can link where it's coming from. For example, sulfur emission, you know that it comes from sulfur in the fuel, right? Particulate matter that based on ash content, CO2 emission that come from carbon content, and so on. For example, this one is the emission factor of the SO2. You can calculate by the amount of sulfur content in the fuel, and then we need to multiply 2, because when we're talking about sulfur molecular weight is 32, and then when we're talking about sulfur dioxide emission, molecular weight is 64. That's why we need to multiply 2 here. It's the concept of the mass balance, like mass input equal to the mass output. And then this one is the adjustment when you have some of the sulfur that retain in ash, it will not go into sulfur dioxide. And the third one gonna be some formula that you can use to estimate emission if you have more detailed information. For example, this one, if you have monitoring emission from the same method, like the continuous emission monitoring from the stack emission, you can use this equation to calculate. Like the total emission gonna be hour of the operation multiplied with the emission flow rate, multiplied with the concentration that you get from the same data, and then multiply with the actual day that the point source are operate, and then 10 to the power 9 is the adjustment changing your unit to ton per year. Okay, so this is 3 simple formula that you can use to develop emission inventory. Anyway, the complexity of the emission inventory can be more when you add more factor into the development. Okay, talking about the data requirement, we're gonna talk not into detail, but I'm gonna provide some of the examples so that you know what should be the data requirement for different tiers of the emission inventory development, for point source, for area source, and for the mobile source. Before going to the example of different tier requirement, when we're talking about methodologies, I talk about this a little bit, about tiers of emission inventory. There are 3 tiers. Tier 1 gonna be less detailed inventory. Usually we're gonna talk about top-down approach, right? Starting from national level information. Those gonna be considered as tier 1, less detailed inventory. Tier 2 gonna be more detailed inventory of the source, usually when we consider in our calculation with different technologies. Like for example, if we're talking about car with Euro 1, Euro 2, Euro 3, and then we classify those car technology in our emission inventory, those gonna be considered as tier 2. And then for tier 3, gonna be the more detailed inventory. The most detailed inventory, which gonna be the bottom-up approach. We're gonna see, look at the example of each individual source. What are tier 1, tier 2, tier 3 data requirement? Okay, first for the stationary source, for the stationary point source, for example, emission from the stack of the factory or maybe from the power plant. For the tier 1, meaning that less detailed inventory, you can use the information of, like for example, consumption of different fuel type. What is the consumption of the coal, what is the consumption of natural gas that used in the factory. And then the emission inventory gonna be default emission inventory, default emission factor that only based on the fuel type. For example, how much particulate matter that come out by burning 1 kilogram of coal, something like that. And then if we go higher to the second tier, now we have the technology include, right? For example, the information gonna be how much coal that you burn in fluid based combustion or different type of combustion or something like that. And then the emission factor requirement gonna be technology specific, right? The fuel based, like fluid based combustion, what is the emission factor? Tangential fire, what is the emission factor, and so on. For tier 3, for the point source, the data that you need to collect from the tier 3 gonna be the data that you collect from SEM, continuous emission monitoring, that are specific for that particular factory. And the emission factor gonna be very detailed, right? Correspond to the same data that you collect. Okay, moving to the second source, which is gonna be area source. And then you can see that for the area source, the emission tier can be only go up to the second tier. We don't have third tier for the area source. Different type of area source are listed here, but I'm gonna give example for the domestic emission or maybe residential combustion. For the residential combustion, the activity data that we can collect gonna be maybe the fuel type for the tier 1, like how much fuel wood are used in the household. For the tier 2, gonna be both fuel type and combustion technology, like what is the stove type, maybe the improved stove or maybe traditional stove that use, and then emission factor also needs to be correspond with this kind of the activity data that you collect. Okay, for the mobile source, the activity data and emission factor gonna be based on this information. For the tier 1, for activity data, we can use fuel consumption. And then for emission inventory, emission factor gonna be the bulk emission factor. This one, I think I already used this example several times. How much maybe gasoline are used in the transportation sector. And then what is the particulate matter emission by burning 1 kilogram of gasoline, something like that. For tier 2, we need to have more information, like the number of vehicles and also maybe the technology of the vehicle. And then the emission factor is going to be depend on different technology of the vehicle, like Euro 1, Euro 2, Euro 3, going to have different emission factor. And for tier 3, going to be more detailed information. For example, going to be the emission that relate to different speed of the vehicles. Like at the lower speed, the emission going to be higher. While when the vehicle travel with higher speed, then the emission going to be lower. And then the activity data need to be more detailed also. How much vehicle gonna be driving with this constant speed over some specific period of the time or something like that. Okay, so this slide show the example of the emission factor for different tiers. And then the one on the top is the example of the point source. You can see that this one comes from the WHO data. The manual from the WHO that they provide this emission factor for the power plant, that okay, if you use fuel oil, this is the emission factor that you can use. If you use anthracite coal, this is going to be the emission factor that you can use. But you can see that it will not differentiate by different type of technology, so that we consider this as tier 1 emission factor. For EMAP, EEM, and for the AP42, you can see that the emission are classified by the combustion technology. Like normal firing, you use this emission factor. Tangential firing, you use this emission factor. So when we have the emission, when we have the technology involved, then the emission are classified as tier 2 emission factor. For the point source, the tier 3, as we discussed, going to be data for SEM, which are specific for the factory. For the residential sector or the area source, you can see that if we are talking about the emission factor from the fuel wood, different type of fuel, then this one can be considered as tier 1. And if they have the information on the technology, for example, on the top is fuel wood, meaning maybe traditional stove, and then the below one is fan, mean improved stove that include the fan to improve the efficiency by adding more oxygen into the combustion chamber. In this case, we consider as the tier 2 emission factor. On the right hand side, you can see mobile source emission. Tier 1 emission, for example, passenger car emission factor equal to this amount gram per kilogram fuel. For tier 2, you can see the emission of passenger car by different subcategory of engine standard, and then they have emission factor correspond with those emission standard. For tier 3 are more detailed. This one also the emission that come out from van, truck, different type of vehicle. Different line of this refer to different engine vehicle type, engine standard, pre-Euro, Euro 1. And then different dot refer to the emission that come out at different speed of the vehicle on road. Okay, so when we talk about good practice principle for emission inventory, it needs to be transparent, meaning that all of the assumption and also all of the methodology that you use in developing emission inventory need to be identified and explained in maybe in the subsection of the emission inventory. And the emission inventory need to be accurate, right? Usually we don't know whether your inventory is accurate or not accurate, but we should have some level that, okay, your emission inventory should be in the unit of maybe teragram or 10 to the power 6 gram per year or something like that. So it needs to be not over or lower than that level. And then it needs to be complete, meaning that it should cover all of the sources that are important in your study area. And then next one is it needs to be consistent, meaning that the inventory that you develop maybe from this year or maybe for this location need to be on the same method when you develop in the previous year, or maybe that you develop for the other location, so that you can compare the data among different studies. And then it needs to be comparable, meaning that when you develop the emission inventory, it needs to be compared with other study. Okay, these are some of the typical error in the emission inventory development. First one, you're missing some source. It may be okay if you're not missing the major source, but if you're missing the major source, then it's going to be the problem in your emission inventory. The second one also very important, double counting, right? Forest fire in some location, they consider as the man-made emission. Then if you develop the anthropogenic emission, then it will not include in your study. In some country, they also classify forest fire as human-made because human may induce the process or the rate of the forest fire to happen. So you need to check this kind of thing. You don't need, you will not double count of the source in your study area. Next one gonna be improper source location data, right? This one you don't know exactly where source are located, and then you put it into the wrong location. Next one is the missing technical data. For example, you don't know what is the emission control technology that the factory use, and then you use different or maybe wrong emission factor that correspond to the control technology that is not suitable for the existing factory, then the emission inventory going to be wrong. Last one going to be the erroneous technical data, including the misinterpretation of the emission factor application, meaning that sometimes we didn't develop the emission factor by ourselves. We use other data source. Then we need to make sure that the situation that we apply the emission factor from the study, from other study, going to be the same as the situation that we apply in our study. Okay, last slide going to be talking about verification of the emission result. The emission inventory should be verified in order to check the correctness. So the verification include comparison with other study. It also includes the back estimation, like you can use the same methodology that you use now, use in the data that you developed in the previous year and check whether it's correct. And also you can compare with other estimate. Maybe use other approach, like check from the ambient concentration by maybe using some of the inverse modeling approach. For example, you put emission inventory into the model, and then the model estimate the concentration, check whether the model, the concentration from the model are the same level as the monitoring data. Or maybe you can use the receptor model that can also give the information about the source. But I put here as the warning here that, okay, emission inventory only include the source in your study area, while receptor model may include the source that are outside of your study area, right? Because receptor model, when you collect the data, it means that maybe the source that are outside your study area but contribute to the concentration in your study area can be represented in the receptor model. But anyway, you can use this kind of the information from receptor model to also compare with the emission that you have developed from the emission inventory. And then with the next two slides is the information of the emission factor database for your information. This one is some international emission factor database, and the last one going to be some of the web resource on the global and regional emission inventory. So with that, I would like to end my presentation and welcome any question that we have. Thank you.
Thank you, Dr. Gordon, for your nice presentation on emission inventory development process and emission factors. It was a quite informative presentation. Now, may I request the participants to write your questions on Q&A box. There is a clarification basically from a participants that emissions of a particular source from a place should be different from emissions of that particular source in other place and area. So that means we need more and more emission inventories for a country and more emission factors for different places and sources.
Right. I think that is very important, and then I think it's good that the participants point this out. The emission, the same source in different countries gonna be, in different location gonna behave differently. For example, if you have Euro 1 in Thailand, not gonna be the same as Euro 1 in Europe or something like that, because of the condition that we use the cars, the traffic condition, and also the maintenance approach or something like that are not going to be the same. So the information that we need to develop the emission inventory need to be developed locally. For example, the emission factors need to be developed locally, and also the activity data need to be collected on the local scale. Yeah.
Any more questions from participants? Sometimes the fuel, say diesel, is adulterated and have very high emissions. In that case, how to incorporate calculated emission inventory and emission factor for that?
Okay, so I think this is a good example of that. That why we need the local developed emission factor, because if we develop the local emission factor, then meaning that the condition of the fuel that we use gonna be represent whatever the actual fuel that we use in that particular area. And most of the time, if you want to specifically study some of the fuel that are not the same as the common fuel, then we're going to be bringing those kind of fuel put into the cars, and then use chassis dynamometer to study the emission factor. and use that information to develop the emission inventory. So to answer simple question, answer the question is we need to develop the emission factor, particularly for that kind of the fuel.
I have question from my side. Since the emission factor estimation is very complex process, you need a lot of. So, is there any kind of simple method to or simple instrument which like hand carry instrument that can be used for the emission factor estimation?
So
maybe vary parameter to parameter.
Yeah. So yeah, I think that's a tricky question. I think there are some equipment, handheld equipment that we can use to monitor the pollution that coming from the source, right? And then we can use that to convert back into the emission factor. Anyway, I think there are some note that I would like to put here that not all pollutant gonna be able to do like that, because some pollutant gonna be changed quickly depend on the situation or the condition of the engine and also the measurement. So you need to be aware of that. And also this method under the not control environment, maybe there's some high uncertainty involved in it, so that when we develop emission inventory, maybe we need to incorporate that, okay, this is gonna be have some kind of the high uncertainty associated with the emission inventory development in this process. But anyway, I think that might be one of the example that we can increase the amount of the data source of the emission factor that we have.
How to estimate the emission factors for non-point sources? For example, biomass burning. It's difficult to estimate the amount of biomass burned. So in that case, what is the like kind of easiest method to estimate the emission factor?
You mean emission factor, right? So in that case, the emission factor, we just collect the data. We bring the dry residue that you're interested. For example, the crop residue, you just bring it to the lab, burn, and then collect the emission and then calculate emission factor. But in the field, if you want to estimate how much emission that come out from the whole field, that you need to estimate how much dry mass are generated or something like that, we have some approach, and I think maybe Dr. Didin may include in the next presentation about that.
One more question. It is difficult to count the vehicles using adulterated fuel, like in a Indua 3 wheelers generally use adulterated fuel, and counting is really difficult.
Sorry, can you ask again?
The question is, it is difficult to count the vehicles using adulterated fuel. I don't know what's the meaning of this, but like in India, three-wheelers generally use adulterated fuel, and counting is difficult.
Yeah, so I think the emission inventory development, I think the process need to be update every year or every time, so that maybe at the beginning you may start with the simplest one, and then later you do more interview that what is the type of the fuel that you use, and then with that information you can update that information into your existing emission inventory. The same in other country, sometimes they don't use only one type of fuel. Right now we have hybrid, right? Sometimes they use electricity, sometimes they use diesel or something like that. So we don't know what are the types. So this kind of information need to be, we need to do interview in order to collect those kind of information and incorporate into the emission inventory.
Yeah, all right. Since time is not permitting us to bore more questions, if participants have more questions, just email to me. I will pass those questions to Dr. Borden and he will reply you later. So thank you so much, Dr. Borden, for your nice presentation.
Thank you very much.
Yeah. Now we move to the second presentation of this module, emission inventory development. The next presentation is from Dr. Didin Augustine Parmadi from the National Institute of Technology, or ITENAS, Bandung, Indonesia. Dr. Paramadi is a lecturer at the ITENAS, Indonesia. His research is mainly focused on application of three-dimensional chemistry model, transport model, emission inventory, environmental impact assessment and monitoring, and air pollution, climate change linkages. He published many research papers in highly reputed journals, including 16 books, chapters. He has served as a trainer in many international training in the fields of emission inventory and air quality monitoring and modeling. Professionally, he is engaged with the international scientific communities as reputed scientist and a member of the International Global Atmospheric Chemistry, that is IGAC, the Asian Network on Climate Science and Technology. Dr. Didin, the floor is yours.
Okay, thank you so much, Dr. Verma, and good afternoon to all of us.
We cannot hear you properly. Can you close to the mic?
Can you hear me?
No, we cannot hear you.
Okay. Can you hear me now, Dr.
Yes,
Verma?
yeah, we can hear now.
Okay. Yeah, thank you so much for nice introductions. And also we would like to greet you all. Good afternoon to all of us in this capacity development program on air quality management and emission reduction of PM 2.5 for Asian countries. My name is Didin. So I am now based in Bandung, 2 hours drive from Jakarta, and I'm recently the lecturer in environmental engineering of Institute Teknologi Nasional Bandung. So in this session, I would like to have 4 main parts actually. The first one has been well covered by Dr. Ekbordin. Thank you so much. It's about the emission inventory basic and process. And then we will come to the second part of emission inventory tools and some case studies, of course, using those tools. And the third one will introduce some of the available emission models, and most of them are source-wise models actually, and we will present you some case studies related to their application or implementation. And the last one, of course, one participant asked a question, very good question, on how to reduce the uncertainty of emission inventory results. So then the last part, I will talk about the uncertainty analysis of the emission inventory results. Okay, so I think all of us getting more familiar with emission inventory, as has been well presented by Dr. Ekbordin earlier. So by definition, by the US EPA, emission inventory, or EI, is a comprehensive listing by sources of air pollutant emissions and their relative strength in a geographic area during a specific time period. So we know that there are 2 important dimensions here. The first one is the spatial information, and the second one is actually about the time. So this is the basic equation on how to do the emission inventory. So this is one of the big difference between air pollutants emission inventory and the greenhouse gases actually, because in emission inventory for some particular sources, we need to include the information of the control efficiencies. Yeah? For example, for power generation, you may have electrostatic precipitator or maybe cyclone. Then we need to input the value of control efficiency in the estimations. Okay. Yeah. So why do we need emission inventory? And often the policymakers, they may have these questions. The first one is, what quantities of air pollutants are emitted in a specific area, and where do they come from? And then the second question may be related to which activities or sectors are the largest emitters of pollution. So we talk about the primary sources actually. And then what type of emissions are currently controlled and how well are they controlled? So this kind of questions can be relatively answered if we have good data of emission inventory. So why don't we take a look the success story of United States of America? So when they have been doing the iterative process of air quality management by the US EPA since 1970. And as we can see now, the city of Pittsburgh is getting cleaner and cleaner as compared to the 1950s, for example. So the US EPA has conducted emission inventories since a long time to determine the emission reductions. This will help the policymakers to develop programs to achieve, and then of course to implement and enforce strategies actually through the source comply, permits, and enforcement. So then this cycle of air quality management is so dynamic. So then including the emission inventory tools actually, which can be always improved time by time. So I think this question also have been well covered by Dr. Ekbordin, that emission inventory have several benefits, but the inventory cannot tell us these three things actually. I think the distance of air pollutant emissions that are transported, this can be only known by using modeling. And then the amount of air pollution to which people are exposed, this cannot be also known by seeing the emission inventory data. The health risk from the air pollution and secondary air pollutants are among of the factors or information that are not that cannot be clearly explained by using the emission inventory data. Okay, sorry. So for emission estimation, US EPA provide guidance for the estimation methods. So I think different emission inventory guidebooks or manuals, they arrange this estimation method in the tier level actually. So for example, for point source, of course, using the continuous emission monitoring data will be the most accurate estimations. And then one may use the source test, material balance, and also the traditional emission inventory methodology by multiplying the emission factors and activity data. So these are some possible methods to estimate or to calculate the emissions. And then when we see the key steps in emission inventory compilations, so I think this one also has been explained earlier. We need to design the emission inventory stage, and then we need to collect the activity data and then compile the emission factors. That's why when we take a look at several emission inventory guidebooks, they are quite helpful actually to provide initial information. So it doesn't mean that when you take some data from the guidebooks or the manuals, it is the absolute data that you need to use. But of course, some good guidebooks may provide you alternative actually to supply your own data. And then we can calculate the emissions. As mentioned earlier by Dr. Ekbordin, we need to verify, or if possible, we need to do also the back calculation just to check again as part of the quality control. Uncertainty assessment, this is also one important part of emission inventory. And then we need to think the data presentations and applications for air quality management. At least there are two actors, key actors in EI implementation. The first one is emission inventory manager, the one who need to manage the resources, the one who need to establish the emission inventory team, data acquisition and supervision of the data collection, etc. And then the second team is the emission inventory compiler. The team consists of experts actually who are responsible for compiling and documenting the emission inventory. So in many cases, it is relevant that the EPA may be the EI manager, and then they may appoint the EI compiler, the team of experts who are responsible actually to compile the inventory. So these are other benefits of emission inventory. The first one, of course, emission source contributions. This will be very helpful to prioritize the emission control, and then this data also can be well clarified or maybe can be compared with the result of the receptor modeling, and this issue maybe will be covered by Dr. Viros after these presentations. Of course, it can be used for three-dimensional air quality model applications to evaluate the impacts of control measures. I will just give the example on how emission inventory can be used to evaluate the achievement of one policy measure, and then to evaluate the emission trend, and then also to review the impact of new sources of air pollution. So basically, this one will be under the environmental impact assessment. These resources have been also presented earlier. The existing global database of emission inventory. There are several data sets, and then they have their own features. Actually, they are available for various scale of implementations, and then time period. Also, the coverage of species in this inventory also different from one data sets to others. We remember that before 2005, black carbon and organic carbon are rarely seen in the global database, but now, those important parameters have been presented or included in the inventory data. So from those data sets, you may want to extract the data. For example, this is from Edgar et al. For PM 2.5 in Southeast Asia. For industry, transport, residential, and then the below one, actually, this is the global data set of trash burning provided by Wiedenmeyer from NASA, actually. So as a beginning, when you don't have the emission inventory data, you may want to get the global data set, the existing data sets. And then, of course, the emission data can be the crucial input for air quality modeling application, actually. This is one of the typical framework when we use the emission inventory compiled from the global data source. There are several sources, and then sometimes the data are not well available for PM and VOC speciation. And then if you would like to improve the spatial resolution and also add the feature of temporal variation, then we need to spend some efforts to provide the ready input emissions to be supplied to the air quality modeling applications. So just to note that emission is a crucial input for air quality modeling applications. These are available emission inventory manuals, EMAP-EA from the European Environment Agency, and also we have also the GAPF from Stockholm Environment Institute, and then also the atmospheric brown clouds emission inventory manuals as part of the collaborations between AIT with previously UNEP RRC.AP and now AIT RRC.AP. So these manuals are available online, and then some manuals also have been accompanied with the compiler or maybe some tools, and mainly available in the Excel format. Yeah, so this is the atmospheric brown cloud emission inventory manual milestone. Actually, the activity was started with the expert group meeting in May 2008. Yeah. The team consists of Professor Kim and also Professor Ramsresta from the Energy Department, and also Dr. Maheswaru Paketi from RRC.AP, and then some experts like Dr. Heri Valak and Dr. Tamibon, yeah, were invited in the meeting, yeah, to identify the key data, key sources, and key pollutants, yeah, to be included in the manual. And then also the experts, invited experts, provide inputs, yeah, to the manuals, including the detailed structure, methodologies, and also the compiled activity data. And then the activity was continued to November in 2008, yeah, to have international workshop. And then we invited many emission inventory experts from several countries. Yeah, the aim is to review the draft of manuals and then to assess the status of data availability in the mainly in the developing countries, and then to facilitate interactions with various regional and international experts. Yeah, of course, the main aim is to improve the document. So this is the structure of the atmospheric brown cloud emission inventory manuals. So totally it consists of 11 chapters. Open burning sector includes 3 chapters of crop residue open burning, forest fires, and municipal solid waste open burning. And then the non-open burning sector, it includes 5 chapters actually. And then the remaining part of this document includes 3 chapters, yeah, like introductions, and then the inventory methods and coverage, and also the user's guides, yeah, for the ABCEIM Excel workbook that come together, yeah, with this manual. Yeah, this is the appearance of ABCEIM Excel tool. So we intentionally provide in Excel tool because this is one of the most user-friendly tools for everyone. So we hope that perhaps the people from EPA can also use these tools, yeah, to compile their own emission inventory. So we have the page navigation, and then when we click to the particular or selected source, then we may have this kind of Excel worksheet. Yeah, so then we can select, yeah, the particular sources of interest, and then we can learn what kind of input data, and then some emission factors are by default, yeah, provided, yeah, in this Excel worksheet. But of course, we also provide a chance, yeah, when you have your own emission factors, yeah, to be supplied in this Excel tool actually, just to ease your work, yeah, to compile the emission inventory. This is one of the example of the case study for emission inventory in Indonesia for the year of 2010, and we have published this work in Atmospheric Environment. So we would like to assess actually the emissions of air pollutants and greenhouse gases in Indonesia, and then the impacts of national policy for elimination of kerosene use in cooking. This is one of the largest energy program actually have been conducted in developing countries, because the government, they would like to replace actually the kerosene use in residential sector, and then replaced by LPG. So this is one of the typical data or results of emission inventory. We can present the relative emission strength from various sources for different type of species covered in the inventory. Yeah, for example, for PM 2.5, yeah, it is mainly dominated by the residential combustions. As we know, in 2010, that the forest fires was not intensively occurred that time. So from year to year, actually, the dominant sources may change. Actually, it depends on the occurrence of the activity. And we can also present the emission in a spatial distribution like this. So for example, for PM 2.5 and NOx for Indonesia, we present the emissions by cities. Yeah. So from almost of 365 cities in Indonesia, we can plot the emissions, yeah, for each city. This is just would like to emphasize that emission inventory can be used to evaluate, yeah, the policy. For example, this zero kerosene program, yeah, in Indonesia, because the government would like to phase out the kerosene use in the cities and then replaced by LPG. Yeah, because before 2007, kerosene was the main fuel, yeah, for households and fisheries, because this kind of fuel was heavily subsidized by the government. But the subsidy actually did not reach the end user, and many times it was diverted actually to industry and commercial sector. So through the presidential decree number 104, 2007, then this policy was firstly promulgated that time. So as we can see, the fuel consumption of kerosene in resident sectors will be reduced, yeah, time by time, and then replaced by LPG, yeah, because we know that the energy equivalent, yeah, for 1 liter of kerosene is equal to 0.6 kilogram of LPG, and then the government also tried to learn, yeah, from some neighboring countries, yeah, for example, in Malaysia and also in Thailand. So we have 3 phase, actually the beginning of the program, and then the base year of emission inventory, and then the end of the program. So we would like to know whether we will achieve some net emission reduction or not, yeah, from both air pollutants as well as greenhouse gases. So as we can see here, varied by species, we estimate the net emission reductions of kerosene use and then LPG use, yeah, from 3 different periods, and then estimate the net emission reduction. Yeah, for example, for PM 2.5 and PM 10, yeah, we achieve 35% reduction, yeah, from the initial emission in 2010, actually, for the base year. And then also the ABC EIM was used to compile the emission inventory for Jakarta, yeah, in 2019, because we have one program on Jakarta airshed source apportionment. So through this collaborative works, we would like to see actually the impacts of different sources on air quality in Jakarta. So this is one of the collaborative efforts, yeah, with the Center for Research of Energy and Clean Air, with ITENAS, as well as with AIT, under the leadership of Professor Kim. Yeah. So this is also one of the typical emission inventory results for Jakarta, showing the different contributions of different particular sources included in the inventory to the total emissions of all pollutants. Yeah, and of course, if you would like to utilize the emission inventory data for various purposes, yeah, for example, modeling applications, then we need to have some spatial distributions of the emission. This is the example of PM 2.5. Using the OpenStreetMaps, then we can allocate the traffic emissions, yeah, following the road networks in the area, actually. Yeah, but again, for particulate matter emission inventory, we have several challenges. Of course, the first one is the particle size. It determines the transport and depositions properties. So that's why we really need to well resolve, yeah, the size of particulate matter. Yeah, it should be well define actually between PM2.5, PM10, or whether it is TSP. So therefore, we need to select the right emission factors for that. And the second issue is related to the chemical composition, the fractional abundance of particulate, which is normally required for air quality modeling applications. Yeah, as we know, the chemical components in emission can vary by sources. For example, black carbon, organic carbon, and also particulate nitrate, particulate sulfate, etc. So to represent the formation of secondary aerosols, of course, the other precursors, should be well estimated. For example, NOx, SO2, and ammonia actually should be well presented in this inventory activity. And then, as we know that for a short atmospheric lifetime, for spatial distribution is good enough to tell actually where does it come from. And then for temporal variation, for hourly, daily, weekly, of course, this is very complex actually, because the impact is big, but we don't have enough knowledge actually to resemble all of these factors in this air quality modeling application, for example. Okay, so the next part, just would like to give you some highlights of the available emission models actually. The first one for transportation sectors. Just to give some example that you can also use these tools to compile an inventory of on-road mobile transport in your city, for example. We have a tool named as International Vehicle Emission, or IVE. Or maybe if you would like to estimate the emission from the airport. So we have one quite handy tool actually to estimate the emission, and at the same time you can also have the dispersion of the emission from the airport, and at the same time also you can estimate, or you can model the noise level of the activity course available in the airport. And the second thing, we have the LANGAM model, actually, the landfill gas emissions model, so which is quite useful. And then for those who normally do the ozone modeling in one city, perhaps the biogenic emission is one of the important factor. Then we can use also one model named as GLOBASE, but however, the community support on this model was stopped since a long time, but of course it is still useful to, if you would like to try to estimate the biogenic emission in your city or in your province, for example. This is the IVE models. So basically this is the database models developed by University of California, the Center for Environmental Research and Technology. And this is the free model. Actually, you can download from this website. And many experts say that it's suitable actually for developing countries. Why? Because many technology indexes from pre-Euro to Euro 5 is relatively matched actually with the current situations in developing countries. And then as the main features, these models is not using the average speed anymore to estimate the emissions from the traffic, but rather using the VSP, vehicle specific power, or it shows actually the power demand on the engine during driving, tooling with the exhaust emissions. So to have this VSP, we need to have the second by second speed values. So we need to conduct the GPS survey actually to get this data. So actually the challenge is many efforts to collect the data and technology index matching, but in the tiered emission inventory is located in as the first or the most reliable method actually to estimate the emission from transport. You can also see the details, one of the publications here related to the IVE implementation in Bandung in Indonesia. So for IVE input data, we need to collect the data of parking lot survey. So in this parking lot survey, we actually record the odometer reading. So then we can have this kind of data between the age and the odometer reading. So we can know the average age of passenger vehicle, for example. In Bandung, Indonesia, the average age is around 5.2 years. And then we can know also the VKT. This is one of the crucial informations when we would like to compile emission inventory from on-road mobile source. And we found out that the VKT of passenger cars is around 37 kilometers per day per vehicle. And then, as I mentioned earlier, to produce the vehicle specific power, we need to conduct the GPS survey. So this is actually the GPS speed of different road networks actually. Of course, when you have traffic jam, then the speed shows the low value actually. So these are the data, and of course the traffic counting is also important to supplement the data as an input for IV. And then the fleet technologies, we conduct the survey to find out the percentage of the engine standards for different type of vehicles running on the street in Bandung City. So for example, we need to know the percentage of technology here for passenger car actually dominated by Euro 1 and Euro 2. And then they use gasoline, around 93%, and only 7% from the passenger car use diesel oil. So this information needs some tremendous efforts actually for survey in the field, but it can be done because this is very important input data for traffic emission models. And then the models will produce the composite running emission factors for different type of vehicles and also for different species in gram per kilometers. So these emission factors actually has reflected the specific traffic pattern in the city as well as the combinations of technology index for different type of technology index presented earlier. So this is the typical results of the emission inventory compiled for a city. So we can see the contributions from different type of vehicle fleet to the total emissions of different type of species here. For example, for CO and VOC, motorcycle contributes significantly, while for PM, black carbon and organic carbon, the bus, because they use diesel actually, so then they contribute a lot to the particulate emissions. And another tool is the Aviation Environmental Design Tools, or named as AEDT. It's developed by the Federal Aviation Administration. And then you can download the AEDT documentation and FAA guidance on this official website. We use this model because by regulations from the International Civil Aviation Organization, actually they mandated the Ministry of Transport to use these kind of models actually. So we need to have the database of airport database related to the engine of the aircraft engine, and then the facilities for ground handling, and then also the infrastructure in the airport, as well as the land side transport actually in the airport. So this ADT will calculate the emissions, and then at the same time, the model also has an option to conduct some dispersion modeling actually. The algorithm was taken from air mode, actually, the well-known dispersion model from US EPA. So at the same time, the model will produce the emissions and dispersions, as well as the fuel and emission inventory, also the noise contours, yeah, for the aircraft activity. So this is some features in these models. Yeah, we need to really input the detail type of aircraft. So we need to survey to the airport and then collect the landing and takeoff information. Also to see the type of aircraft actually landing in that airport. Yeah, this is the model is quite handy actually because it's in Windows based, so it's quite user friendly to be used. This is one of the example for case study in Soekarno-Hatta International Airport in Jakarta. So we estimate the emissions from aircraft engine and then also from ground handling. So for example, when the aircraft approach the terminals, of course, several facilities should be provided, towing, etc. And then the airport utility, like power generation inside the airport, and also the land transport, from the traffic activity from the passengers. So as we can see here from the results, that the aircraft engine dominates the total emissions in the airport. So at the same time, also model generate the dispersion of the emission. This is example for NOx, I think. And then the figure to the next one is the figure of noise contour actually provided by the AEDT simulation. So I think this is quite a simple model to estimate the methane generation from the landfill. Yeah, basically it's quite a similar algorithm with the IPCC, but there are some difference on how to write the codes following the first kinetic order of methane generations. So we use this model actually to evaluate, or to simulate a different option of methane emission reduction measures before mitigation. This is without any intervention, from time to times. And then there are three types of mitigation introduced, and then using this land game, we can try to estimate the emission reductions actually as compared to the baseline. And at the same time, we can also conduct dispersion modeling using the emission inventory, using land game, using the air mode model, for example. As I have mentioned earlier, this is the one example of the tools named as Globase. I think Dr. Ekbordin also mentioned we have several tools actually to estimate biogenic emission. And then for global scale, they use the Megan model. And then this one may be more applicable actually for city level. So we just need to extract the meteorological parameters from the mesoscale meteorological model. And then we, of course, we extract also the important input data of land use available in a city, for example. And then we can run this model to estimate the biogenic emission like terpene, monoterpene. Those are very reactive VOCs actually. Once they emit NOx or hydrocarbon, then it will be highly potential to form ozone in the atmosphere. I think I come to the last part of my presentation. So this is related to the uncertainty analysis. So mainly Monte Carlo simulation was used. So it's based on the probability density function, actually, the PDFs of all of the factors involved in the emission calculations. So the PDFs explain the range of potential values of a given variable, and the likelihood that different values represent the true value actually. So when we have the raw data, and then the model can choose actually, or can fit the PDF for emission factors and also for the activity data. And then we can run Monte Carlo simulations, and then to calculate the confidence intervals, like 95% confident or maybe 90%, and then we can calculate the percent of uncertainty using the Monte Carlo simulation that can be iterated for 5,000 or maybe 10,000 simulations. So this is just an example. I extract again one of our data from the previous publications, and then normally we use @risk, but maybe you can use another models like crystal balls from Oracle, yeah, to conduct these Monte Carlo simulations, and then we can quantify the uncertainty. This is as an example for municipal solid waste open burning in Indonesia for different type of pollutants actually. So I think in the last part, just would like to have summary that emission inventories must be as reliable as possible. It should be transparent, trackable, and then it should be well documented. And then emission inventories need to be regularly updated with proper documentations. So if you use some kind of EI tools for compiling, like ABCEIM, GAPF, or other tool, then it may help you actually to have the good documentation. And then later on, when you decide to have some improvement of the emission inventory calculation, then you can see again the documentations. The development of emission inventory needs considerations for quality assurance and quality control. Of course, it should be actually integrated in the emission inventory plan. And then we should also consider our relevant sources of air pollutants, like, for example, the species coverage, and then the temporal and spatial distribution of emissions. And last one, we know that there is no perfect emission inventory. So I think don't worry, you just see what are the available resources, yeah, to start as soon as possible the emission inventory compilation in your region, in your city, or maybe in your province. So by that, I would like to end my presentation, and thank you so much for your attention.
Thank you, Dr. Again, for your nice presentation on emission inventory tools. It was quite informative and very impressive. Now, may I request the participants to put your questions on Q&A box. There's already a question from participants. It is about how often the workbook ABC emission inventory guidelines has been updated. What is the latest version of that ABC emission inventory guideline?
Yeah, I think, frankly speaking, that it has not been updated since 2011. So I think it's still in the version 2.0, or yeah, I think since the very first version came up in 2009, right? Yeah.
Dr.
So
Dylan, we have to work on this one.
Yeah.
Yeah.
Yes, yes, I think so.
It's our job to update.
Yes, yes. So I think there are more available of emission factors actually in this region, I believe. So then we can, or we need to incorporate in this ABCEIM. And also for uncertainty analysis, so far, we have included a very simple approach actually for like quantifying the uncertainty, but of course now we can also have more advanced Monte Carlo simulations, for example, to quantify the uncertainty.
Yeah, this could be our next potential project.
Yeah.
There is a question from participants. I think it was related to the previous question, but it's also have a relevance to here. From which source we can get the recent data on emissions about the world?
Okay. Yeah, I think the most recently used is EDGAR dataset. But we need to be aware that biomass open burning is not reported in this dataset. And then for biomass open burning, you can take from the other sources, actually, for example, from Global Fire Emission Database, GFED. Yeah, so they have normally they always update the database actually from time to times, or maybe from FIN, yeah, from NESA. You can also extract the emission. Yeah, it's a global database actually.
Yeah, actually, I'm taking some questions from previous presentation because both presentations are quite similar, quite relevant. So, what are the main guidelines to estimate the emissions?
Yeah, of course, for greenhouse gases, yeah, you may need to see the IPCC, right? Because it's related to the compulsory effort, yeah, for country to report their emission to UNFCCC. But for air pollutants, yeah, we don't have yet actually this kind of systematic international reporting. So, but when we follow up the discussion in IPCC, they are now actually very intense to discuss about the short-lived climate pollutants, and then many air pollutants also are included actually. So the yeah, this kind of scheme actually may like force country to compile their own inventory, especially for these air pollutants.
There is a similar questions. Is there any database for emission factors of different country?
Yes, yes, actually, if you see the guidelines, basically, for our ABCEIM, yeah, we always put the note on the source of emission factors, but somehow we cannot really take the country-specific emission factors for different sectors. For example, yeah, for power generation, yeah, as long as you get the same technology of combustion of the boilers, for example, and then you use the typical fuels, yeah, for that power plant, then you can always take the same emission factors from the global data set. So it's not necessarily to be the country-specific emission factors. But of course, for some other sources, right, for crop residue open burning, and maybe for municipal solid waste open burning, we may need to see the country-specific data, right? Yeah, because it will be well affected by the local meteorology, for example, and also the activity from that particular country.
How to reduce the uncertainty in the emission inventories?
Yeah. Yes. So if we see from the uncertainty analysis, yeah, one of factor because when we have the high uncertainty, we have the huge variability of emission factors because like we can say that we cannot take only value and then the available database of emission factors, for example, range from like times or 2 times. Yeah, so then it can contribute to the high uncertainty actually. And then the second thing related to the activity data. So if we see the guidance from IPCC, if we take the data from international source, so it will deal with higher uncertainty by, let's say, 10%. Yeah, then when you take the activity data from the relevant department, then you may have the uncertainty of 5%. Yeah, so of course, this can be improved by using the survey data, perhaps, that will be more representative, yeah, for your own area actually.
What approach normally used, bottom up or top down, for the regional and global emission data preparation?
For global and regional, right?
Mm.
Yeah, so I think mainly they use the top-down data, as I know that for the energy data, they may take it from the International Energy Agency, and then oftenly also some regional database, they took the energy data from the energy modeling. Yeah. So then again, like if you would like to have more details, yeah, like in your own area, oftenly we cannot really do one approach actually. Sometimes we need to combine both approach actually because of the available resources and also the availability of data itself. Yeah.
Okay, there is another question. How to quantify the emissions of road dust?
Yeah, road dust, right?
Yeah.
Okay, so yeah, as far as I know, I think this is also included in ABCEIM, and we took the approach from US EPA. So when we see the equation here for PM 2.5 and PM10, for example, it will be affected by, for example, the silt content, right, of the road itself, and then also the meteorological factors, parameters, wind speed, and also the precipitation. Yeah, so I think many people they refer to US EPA actually for road dust estimation, emission estimation.
Thank you so much, Dr. Didin. It's really your presentation was on time, and really it's nice to hear from you with nice, very nice presentation with very a lot of good information. So thank you so much for presentation.
Yeah, thank you so much, Dr. Verma.
Yeah. The third presentation and the last presentation of this module for today, that's a source apportionment of emissions of air pollutants by Dr. Mohammad Firoz Khan from the University of Malaya, Kuala Lumpur, Malaysia. Dr. Khan is a senior lecturer at the Faculty of Science, University of Malaya, Kuala Lumpur, Malaysia. He is also a visiting professor at the China University of Mining and Technology for a period from 2019 to 2022. His research interest covers a wide variety of topics in air pollution, source apportionment, environmental analytical chemistry, and human health risk factor of pollutants. He received his PhD degree in risk management and environmental science from the Yokohama University, Japan, in 2010, and he published more than 100 journal research paper, book chapters, and a book. Dr. Khan is serving as an associate editor to the Elementa Science of the Anthropocene and Arabian Journal of Geoscience. Dr. Khan, the floor is yours. Khan, we cannot hear you. Please unmute. Mr. Khan, we will do from here. We will unmute you.
Dr. Verma, can you hear me?
Yes, we can hear you now.
Very good evening, and thank you so much, Dr. Ramlal Verma, for your.
Can you make the slide bigger? Not, still not. Yeah, still.
Give me a second, Dr. Verma.
Okay.
Is that okay now?
Yes, now it's fine. Thank you so much.
So thank you so much, Dr. Verma, for your kind introduction. And I have given 1 hour. So I will discuss about source apportionment and emission of air pollutants. Let me start from here. The content I have. Dr. Verma, can you hear me?
Yeah, we can hear you.
I don't know, some reason my screen is not moving.
Select the presentation. Yeah. Yes, now you can. There is some problem.
Right, let me start from here. I need to do something manually during my presentation. The content here I have listed at the beginning. I will briefly introduce our research team. We are working here at University of Malaya. And then mainly I will discuss two subtopics, fundamentals in air pollution. And I will explain under fundamentals in air pollution, what about air pollution, very basic about air pollution issue from local, regional, and global perspective. And then some of the key air pollutant, their potential source, the process or factors contribute to generate those pollutants. And what about their impact on our health and environment? I will briefly introduce to the participant here. And in my second topic, subtopics, the main focus for this discussion this afternoon is chemometrics application in air pollution. I will briefly introduce chemometrics modeling and a few of the very commonly widely applied chemometric model. For example, PCA, APCS, PMF. I will introduce you their fundamentals, their background, and how those model we can make use in our work. And then in the last two slides, I will explain about how the the source we identified by using chemometrics or receptor model, those source, how we can integrate with two statistical function, for example, PSCF and CWT. And that will help us to know their source region. And in the last slide, I will explain you that the source we identified from our experimental project or experimental data, those identified source, how we can integrate with health risks modeling. So this is how my discussion will move on. Let's proceed now. So here, let me explain you in the smaller slide. Is that okay, everyone? If I proceed with the smaller slide, not in full page. Is that okay?
Khan Saab, this is okay.
Okay, so because some technical issue in my computer, possibly. Right, and the work here in our lab, in our group, I'm working at University of Malaya Chemistry Department, and our main focus in our work is on aerosol. Very common term, everybody, I do believe you know, right? And the spectrum of our work in aerosol, this is the composition of aerosol, the composition which has health concern. We are always concerned about air pollution, but not all the composition in the atmosphere or in our ambient air or our indoor environment is not the great concern. Some of them is a health concern. So our focus is on those group of organic compound or inorganic compound. So let me proceed here with the group we have been working here at University of Malaya. This is a small group, few students working with me, and our work mostly on polyaromatic hydrocarbon in volatile or gas form, and at the same time polyaromatic hydrocarbon in the particle or aerosol form. And some of our group students, they are also working on dicarboxylic acid, and also we are working on toxic composition from the inorganic heavy metal or trace metal, and those are the things we are working with. We are moving forward so that we can generate some data, and those data can help our regulatory body here. I believe that many of the participants here working with Department of Environment, Department of Meteorology. I can see many of my colleagues attending here. So this information, I mean, parallel to Dr. Ekburdin and Dr. Didin, how they presented the emission data, how we can generate emission data, parallel to those emission inventory data, the source information data, source specific toxic pollutant and their strength from the source, how they are coming in the air. This is how we are trying to develop some data. So let's move on to the next slide here. And my topics here, the first subtopics, fundamentals in air pollution. Under these subtopics, I will introduce you. Let's move on with this slide, air pollution, right? I do believe everybody, you are familiar with the term air pollution, right? To me, when I talk about air pollution, wherever to my classroom or to any presentation, the impression, first time the impression comes to my mind that it is something not very good for our health, right? This is how the reaction when we talk about air pollution that comes to our mind. The reason is there, obviously, because once we talk about air pollution, this air pollution is nothing but a mixture of particles and gaseous composition, right? That we always breathe in through the air, right? Currently, as we are under a very different condition, right? Currently, we are under lockdown, we are staying at home, and everybody, we are trying to have safer life, right? We want to stay inside home. And we always believe and we have thought that if we can stay at home, the air we breathe in, that would be very clean air. If we can stay at home, the pandemic, the COVID, will be safer from the COVID like infection, right? How about the real situation? It is very different, right? Everybody, we already experienced that. We know COVID, this is airborne. It can transport through air particle, right? Airborne droplet. And at the same time, if we can stay at home, it is also very well established and well in the literature that our indoor, the air we breathe in, the pollution level is much more, about 5 to 10 times high compared to the air if we breathe in from outside, right? Right. And how this air pollution, what are the major sources that contribute to change this pollution, to change the air quality, whatever in the indoor or outdoor? The major source, you can see I have listed some of them. There are versatile sources, so many. For example, mobile sources, stationary sources, area sources, natural sources, right? If we go one by one, it would be a very long talk, right? So I do believe everybody we know, and if we know more, we can get it from the literature, right? And then my second priority is, third priority is some of the key composition in the atmosphere. Those key composition is what? PM10, PM2.5, ozone, oxide of nitrogen, carbon monoxide, sulfur dioxide. Very common, and mostly everybody we are familiar, right? The reason I pick this key pollutant, it is because this key pollutant can help us to know how about our air quality. It can simply give us an impression, the quality of the air that we breathe in. It is a good quality of the air. It is a clean air that we supposed to believe always, right? So these are the key composition can help us. So let us have a details look on this key composition. In the next slide here, you can take a look that in an infograph here, I have classified them in two groups. On the left side, you can see the composition, key composition in the atmosphere, that we can classify them as a primary pollutant. And we have another group of pollutant, not all is pollutant, but atmospheric composition in our atmosphere. Those we can classify them as a secondary pollutant. And how about from the infograph at the bottom, you may have find it easy to understand. I purposely inserted number of sources here, and this source is a primary source, and this source often contribute to change the concentration of this pollutant in our atmosphere, and then change the air quality, the air we always breathe in. And then on the right side, the secondary pollutant, those secondary pollutant is mostly coming from the precursor of the gases or the particle, those coming from the primary sources. And there are a number of atmospheric processes keep occurring. For example, heterogeneous chemical reaction, photochemical reaction, physicochemical reaction, many processes, those processes contribute to generate a number of composition, for example, sulfuric acid, nitric acid, ozone, right, ammonium, and then some of them also contribute to generate secondary aerosol particle. And one more example is biogenic, for example, isoprene, right? If we look through, and if we can go through the literature, we may have the detailed explanation how these processes keep occurring. So let's move on our next slide here. The air pollution that we want to discuss more in details. This air pollution issue, it is not only an issue at our local scale, it is a regional problem, it is a global problem. And if we see the impact of air pollution from global scale, every year about 7 million people died due to the exposure of polluted air, particularly people who are staying nearby roadside or nearby industrial setup, right? And if we look at the bottom left corner, there is a picture here. I purposely inserted some picture to let you know the air pollution issue, how it is impacting in Southeast Asia. For example, biomass burning from Indonesia. Dr. Didin already explained a lot about those, and that biomass burning not only impact in Indonesia, this biomass burning, the smoke from biomass burning is spread over the entire region of Southeast Asia, and that causes the haze. Do you know haze? Haze is an example of air pollution, right? Once a haze appears, so we simply, our very common people, generate people, they have an impression that air quality is not very good one right now. So we should not go outside without masks, right? So this is how we understand that how air quality change. And this air quality, if we look into other Asian cities, for example, in Beijing, participants who are from mainland China, you know, the Beijing haze due to the sulfur dioxide pollution. If we talk about New Delhi, our many participants here from Indian region, South Asian region, you know, winter fog, and also the seasonal biomass burning. And that causes, that integrate with local meteorological factors, and we experience the winter fog. And this is an example also, the air pollution episode in Indian region. And this air pollution episode not only in our Asian cities. Right now, I do believe everybody, you know the news that in British Columbia there is forest fire keep going, and people is moving from their house for a safer place, for a better quality of the air they want to breathe in. So they are moving out from their house. They are going very far, right? If you look into the YouTube, you will find very recent video how forest fire contribute to change the air quality. So this kind of issue everywhere around the world we are experiencing. So let's move on to know more about our region in Southeast Asia. In Southeast Asia, purposely I put this slide that there are always forest fire in Sumatra region, Borneo region, Indonesian Borneo, Malaysian Borneo, both sides. And at the same time, in this region, participants who are from this region, you know that the soil also kind of organic soil, peat soil, and in those all scenario during the dry monsoon time, we often have fire, right? And this fire stay for quite longer time because the fire from the surface or forest that eventually goes into the soil. And then I mean, this scenario causes to have continuous emission of smoke. Sometimes we don't see from the source, but slowly it is keep coming in the air. And it is not only the black smoke, it is also causing to have the emission of greenhouse gases, right? So a number of volatile gases, and then that eventually is spreading, you can see even from the picture and also from the published newspaper headline, how the scenario report in the local newspaper, the smoke is spread over the region. Do you know 100,000 people died in 2015, the biomass burning that occurred in Indonesian region? The exposure from the smoke from 2015, 100,000 people died. This is reported by a research project from University of Harvard. And then later there is another paper from, we also have collaboration from University of Leeds, Dr. Dominic Group. In our paper also, we reported about 44,000 people died due to the exposure of biomass burning from 2015. Let's have a look more about how air pollution scenario from our local region and at the global, regional and global scale, how it impact and then coming in the digital media. Even though this is you have now you have seen that how air pollution scenario from local, regional, and global scale, how people they have been experiencing around the world. So let's move on with some detailed explanation about those key air pollutants. Let's start with airborne particulate matter. And airborne particulate matter, if we want to talk about PM10 or PM2.5, it is always good to know how small their particle size. The PM10, if we want to know their particle size, you can see here a comparison has been made, the cross section of our human hair, how PM10, it is about 1/10 of the cross section of human hair. And then if we want to know the PM2.5, how about the aerodynamic size? If we made a comparison with PM10, you can see how small one particle size of PM2.5 compared to a entire PM10 aerodynamic size, right? So this is the tiny air particle simply can't penetrate through our respiratory system and causes a number of respiratory related problems. Not only the respiratory related problem, this air particle, airborne tiny particle, can causes also the cardiovascular problem, a number of heart related problem many people experience, right? And then apart from this respiratory cardiovascular disease, this air particle even can pass through our bloodstream and coming into our human head or brain and causes brain related disease, neurological disease. For example, Alzheimer's disease. Simple example is many old people in our family, you have seen that they simply lose their memory, right? So this kind of particle, once coming into our brain, can cause those kind of memory loss kind of disease. So let's move on. And one more thing I want to introduce to you, don't want to lose this opportunity, that you have seen airborne particle. The impact is directly on our respiratory system, right? And at the current pandemic, the COVID-19, do you know how it is impacting on our health system? It is impacting directly on our respiratory system. So there is very clear indication that airborne droplet and the COVID, the impact is exactly same. They directly impact on our respiratory system. So there is a very clear indication, and many people is also working and they are trying to prove that COVID even also airborne transmission, right? And so let's move on with other composition, key composition. For example, here carbon monoxide, and I have inserted here few infograph for you to easy to find it to know their contributing source. And all the contributing source here you have seen how CO is coming in the air. Do you know the similarity? It is simple as to everybody that this is a combustion process. And combustion of fuel, many kind of fuel, sometimes solid, coal fuel, sometimes biomass burning, wood, right? Wood is also kind of a fuel, right? So once all the fuel burn, this is simple combustion process. If the combustion process occur, it ended with carbon dioxide. If there is incomplete combustion, CO, carbon monoxide, coming in our air. And how carbon monoxide impact on our health? It is as simple as to me that if we have exposure of carbon monoxide in our bloodstream, oxygen level will reduce. And you know, oxygen level, if it's reduced, or like if there is a change of oxygen level, how that many people is currently experiencing. Once somebody is COVID positive, the first thing we want to know how about the oxygen level. And very popular now, many people, we often buy the oximeter, right? Because we want to know how about the oxygen level we have current right now. So CO, the way it has effect on our health, this is called immediate effect. Once we have oxygen, CO exposure, immediately we will have the effect on our health. But other than CO, for example, particle or other gaseous composition, they have effect, but effect is slow effect, like long-term effect. So let's move on with other key composition or key phenomenon in the atmosphere. Here, one more thing I want to introduce to you, photochemical smoke. Do you know photochemical smoke, once it occurs, it causes to have high concentration of ozone, oxide of nitrogen, and many gaseous, many acidic composition, for example, sulfuric acid, nitric acid, or peroxyacetyl nitrate, many hydrocarbon, oxygenated hydrocarbon that form through this photochemical process. And once those photochemical process occur in our atmosphere, we often experience brownish kind of haze, right? I will explain in the other slide. And impact, I'll explain here. Ozone, you already familiar about ozone. And everybody, we know that ozone, even 16th of this month, September, ozone day is coming. We'll celebrate ozone day, right? And ozone, everybody, we know ozone is very good for our environment, right? Yes, that is good for our environment, but in the stratosphere. In the stratosphere, ozone protect coming the ultraviolet radiation in our Earth's surface, because those ultraviolet radiation is very harmful for our health. So stratospheric ozone is very helpful. But if we talk about ozone at the ground level, at the surface level, ozone causes problem on our health. Ozone impact on our plantation, on our farming, right? our crop production become reduced. Ozone, in that sense, at the surface level is a pollutant, right? So let's move on. Next slide here. Some of the precursor of acid gases, acidic composition in the air. Those precursor gases is what? Sulfur dioxide, oxide of nitrogen, right? Through the photochemical process in the atmosphere, these precursor gases generate acidic gases, sulfuric acid, nitric acid in the atmosphere. And once we have these acidic gases in the atmosphere, through the rainfall, those acidic composition coming in our Earth surface. And now you may have understanding how these acidic gases can cause to change the acidity of our rainwater, and also our surface water, the acidity of the surface water, how that can change. And this acid rain also causes at the surface level on many things, on the water bodies, on the plantation, on our building structure, everywhere it has a damaging effect. So let's move on with the last one here, the volatile organic compound. Exactly same thing. I have inserted a number of infograph here. Those infograph is representing the emission source of volatile organic compound. If we talk about volatile organic compound, it is a very versatile, right? Huge perspective. But if we just make our discussion in a very limit, that we can talk about benzene, toluene, xylene, or part of polyaromatic hydrocarbon which are volatile. Everybody we know benzopyrene is very toxic, carcinogenic. Benzene is carcinogenic, right? And then once this composition coming from this source, coming into our ambient air, not only our ambient air, it could also coming into the office environment. Currently, we are right now staying. So once we have this toxic group of volatile organics or volatile even inorganics, they impact on our health, they impact on our ozone concentration at the surface level, they impact on our respiratory system, they also impact many of our important organs in our human body, right? So this is briefly the fundamental about the key pollutant that we always talk about. We always want to know their level of concentration, because once their level of concentration change, our air quality change, right? So let's move on to my second subtopics, chemometrics application in air pollution. So I want to spend more time on this. If we want to talk about chemometrics, let me start with that. What is chemometrics? How does it work? It is as simple as to me that everybody here, we are researcher, right? Either we are researcher or either we are a student. Everybody, we have our own project we are working with. Currently, we are working with Dr. Verma here under a project awarded from APN, Asia Pacific Network. Many colleagues, we have been working together, right? So we have a goal, certain objective that we want to work with, right? So exactly same thing, the participant here, whoever you are from, you have your own project, right? And once you have your own project, you have objective, and to execute your objective, you set up your experiment, and your experiment that could be in the ambient outside environment, or that could be at the laboratory scale measurement or analysis, right? So all the measurement here, it will give us, do you know what? It will give us a set of data, and sometimes a limited set of data, right? Because if we have limited sample, And if we have measurement in the outside, continuous monitoring, we're supposed to have millions of data, right? And then it is always difficult to manage those data to introduce to an audience like you, or to report in a journal or report in your thesis, right? So in that case, we need some method, model that can help us to summarize our data. So let's move on. This is our objective here. We want to explain you chemometrics model. And chemometric model is, to me, it is exploratory data analysis model. And this exploratory data analysis model not only processes our data, it has application in many spectrum of research. For example, the instrument we make use, to calibrate the instrument, we need to make use chemometrics model. If we want to summarize our data, want to know what about the inventory, right? Our other colleague have been keep talking about many different source, and for many different source, what about the emission factors, right? They have been keep trying to explain, right? And same thing here in chemometrics model, we don't go to the inventory, but we want to know what about the potential source, those sources contributing to change our air quality. So we need to identify. This is called pattern recognition. And at the same time, this chemometric model can also help us to have forecasting. Forecasting means how about the concentration of certain pollutant tomorrow or day after tomorrow, right? We also can do forecasting. This is just simple example how chemometric model has been keep applying to many domain in research. So here I have listed very commonly used model, widely used model, list of model here. If you look in the slide here, left side, PCA, APCS, positive metric factorization model, PMF model. These two model is most widely used model. It is because this two model is very simple, user friendly, right? We don't need to have like information about our data if we want to execute these two model for our experimental data, experimental result, right? On the other hand, there are some other model, chemical mass balance model, unmixed model. There are many other model, but those model is not very user friendly. It is because those model, the input variable is versatile. Those model, we need to also have source information about the data. I will explain maybe in more details in the following slide here. For you to find it easy, I have listed the link for most of the model. If you want to know more, you can go to the link. Some of the link possibly not working. For example, chemical mass balance model, but you are welcome. You are encouraged to read it from the published literature, right? In many research paper, they explain the process, the step, how you can make use all the model, right? So I hope it will help you, our participant here. And let's start with PCA, APCS. How about PCA? What do we know about PCA? PCA is principal component analysis, right? It helps us to make our big set of data into a small set of data. The advantage for PCA is that, but the limitation for PCA is this is a qualitative technique. It cannot help us to group, to make our data in a small group quantitatively. So we cannot use PCA for estimation of contributing source. So what is the way to estimate the contribution of the source? We need to have like integration PCA with multiple linear regression. So if we can integrate PCA with multiple linear regression, MLR, it help us to estimate the contribution for each of the group that we make by using PCA. Still, there is a limitation, disadvantage that this integration PCA with MLR we explain sometime called PCR, principal component regression model. So this PCR model often introduce us negative coefficient factor. So that's negative coefficient physically meaningless. In our data, we work with, this is a data with concentration. So negative concentration, it has no physical meaning. So what we can do, in 1985, Professor Thurston, very famous professor, right? You know, everybody we know. I mean, he come up with a method how we can reduce the negative index from our data. That simple PCA, the conventional PCA MLR, it has very large uncertainty. The group by Professor Thurston, he reduced the uncertainty. He reduced, but not, I would say that 100% we can reduce the error, right? I will explain more in the next slide here. In the next slide, we have given here purposely for you, easy to find it to execute this PCS model. I have given the step by step 1 until step 9. If you follow very carefully, you will able to run PCA and APCS by using any statistical model, any statistical tools. It could be SPSS, JMP, any or Statistica. So you will able to execute PCA, but you have to follow step by step from step 1 until step 8, right? And then I want to give you one soft reminder that before you execute your data by using these statistical tools, you have to clean up your data. On the left side here, yellow highlighted here, this is called pre-processing of your data. You have to clean up your data, then only it will help you, right, to produce some result with less uncertainty, right? Very important for us to reduce the uncertainty. And I have added here, inserted here one more slide for you. You can take a look how you can calculate APCS if you follow from here, beginning with yellow highlight and at the last yellow highlight also, you will able to determine the contribution for each principal component, and that contribution we trust, we do believe that we will have less uncertainty. Right, let's proceed here. Some example application from our group, our student, they often make use chemometrics model. And one example here by Suradi, recently published, and she used PCA, a PCS method. And then if we look into her calculation here, she used a chemometrics model on the concentration of polyaromatic hydrocarbon. And on the x-axis here, you see that the concentration of polyaromatic hydrocarbon that she received from her experiment. And after the calculation by using APCS on y-axis, if we look into this correlation, the correlation R square value is 0.98. So this is giving an indication that the estimation of PAHs by using APCS, it is well correlated. It has less uncertainty, less error, right? And those APCS, by using APCS, we have identified and quantified number of sources here and reported in this pie plot. And this paper already published. If you want to know more about PCA, APCS, you are welcome. to read some more paper from our group that obviously will help you. Not only our paper, there are many other researchers also publishing a paper by using PCA, APCS. Let me introduce you now one of the most important and robust model, PMF. This model developed by using Professor Patero from University of Helsinki. He introduced the algorithm. The key is still with him. If you want to explore more about PMF, want to make some modification, you are always welcome, and you may make request to Professor Patero. He will provide you the key so that you can explore more on the algorithm that he developed. And how about those algorithms? The mathematical form is here that he introduced with a Q value, Q term. This Q value, the way he introduced, we can control the Q value to reduce the uncertainty. Right. So let's move on from here. US EPA later, they introduce a Windows version of PMF. They use the algorithm from Professor Patero. You can also use algorithm by yourself, but the Windows version US EPA introduced by, US EPA, this one is simpler, user-friendly, compatible with Windows until Windows 10. But unfortunately, this Windows version US EPA, it is not compatible with who you are, Mac user, Mac OS, MacBook Pro. So MacBook Pro doesn't support this algorithm. Right, so let's move on. So you all need to download, install on your computer. And I have given here purposely inserted a number of slides. I don't want to explain maybe all, but the slide I have inserted for you to go through because this Windows version of US EPA, this Windows version of PMF require two data file. One is concentration data file, another one is uncertainty data file. An uncertainty data file that we need to calculate by ourselves. So there are a number of ways we can estimate error from our data file, from our concentration data, from our experiment, right? And US EPA, they also introduce in their PDF file some way you can also calculate uncertainty. But there are also many other ways you can calculate uncertainty. We have also reported some in our some papers. You are welcome if you want to know more how you can calculate uncertainty. Let's move on. In the next slide here, I have given a step by step how you can upload your data. If we start from the right, on top right panel here on top, there are two boxes here, concentration data file, uncertainty data file. On the right side here, you simply need to click and locate your data file where you keep. On the left side here, number one, you can see if you click on the right, you will link to your data file. You can go where you keep your data. You can keep your data maybe in a folder in desktop or in your own some other folder. So all you need to upload your concentration data file, uncertainty data file, and then at the bottom, you will see the status of your data file. If your data is compatible, right? So your algorithm can read your data. If algorithm cannot read your data, it will show that no data file, right? Because this algorithm, Windows version of PMF, it accepts data file in Excel form, text file, or CSV file. So you have to do many ways, do some trial and error, right? And then there are a number of input variable here you need to fill up. I do believe that you can, if you look through, you can complete all the initial input variable here, and then you can move on your next slide. Here I have given before you execute your data by using PMF, you need to do some quality control of your data. You can see each of the variable in your input data file. You can click and see their time series, their correlation with one other. If you see there is some strange variable, spike, suddenly very high spike, you need to think about the outlier, right? Possibly your data is not clean. So you will able to exclude or include your data. So you can do that. Once you complete all this QA/QC, you can move on to execute your PMF. On the right panel here, you can start with randomly number of factors, right? So you can put some number. The number of factors or number of factor you want to define, that also depend on, do you know how? It's always depend on how many number of variable you have. If you have like 10 variable, maximum 10 number of factors you can calculate, right? Or less than 10. So you can do some trial and error and calculate Q value, right? I already have shown you Q value in the mathematical equation. And manually, you can also calculate Q value based on your number of sample, number of variable, and number of factors you want to put here. So you can calculate Q value. Once you see the Q value here and Q value you calculated, they are very close. You can think about that this model run could be acceptable, but still you need to follow all the step here. You have to calculate all the way to estimate the error, right? And then go to the next slide here, and you will be ended with number of profile, right? Number of source, number of profile from your data. Randomly, if you run, you will also randomly have some profile, right? It always very important that how meaningful it is for you. Is it the profile you can explain? You have to read very carefully the profile here. If you think that profile 1 and profile 2, yes, you're all variable at the bottom listed here, and then they have a relative contribution into every profile. Yes, there is some similarity based on their temperature profile, based on their chemical profile, based on their physical like properties, based on their unique emission source, right? There should have some similarity, and based on those similarity you can explain, right? So let's move on. If you think that yes, your profile that you generated here is very logical, you can explain them, there is no problem, you can move on, right? You can move on to see every profile. I mean, they have their contribution, right? They make contribution to the dependent variable. For example, our dependent variable is what? It could be total polyaromatic hydrocarbon, or it could be PM 2.5. So how every source, their time series, their contribution by percentage, all you can calculate. Let me show you some example of our in our work that already published in peer review journal. One paper here you can see from our one student already graduated, published in like Chemosphere, and then she has reported number of profile here, factor 1 until factor 4 for, do you know what? For polyaromatic hydrocarbon. And every profile you can see contribution, relative contribution for some of the polyaromatic compound is very different. So they have grouped together, right, in every factors, and then it was acceptable, right, the way she presented and she made discussion. she made comparison, and eventually the work, the project has been published in a peer-reviewed journal. Let me show you some more example here. For example, one more work here. If you take a look here, for PM 2.5, we applied PMF, chemometrics model here, PMF we applied. And then after application of PMF, we estimated PM 2.5 by using PMF on the y-axis, and the PM 2.5 that we measured from our experiment in a certain receptor location. And the correlation here, you may have seen here, the R square value is very significant, right? Well correlated. So it is giving an indication that the PMF, the way we applied here, the PMF will explain the measured concentration by our experiment, from our experiment. So this is how, if you can make argument, your work, it would be acceptable, right? And in similar way, we have identified number of sources and reported their quantitative contribution. And each of the source here in the profile on the right side here, we have explained each of the profile as a source. Do you know why? It is because in every source, the composition contributed for each of the source from the bottom x-axis, there is a similarity. Some of the composition coming under one group, they have a similarity. Possibly they are showing similar temperature profile, possibly they are showing similar chemical profile, possibly they are showing similar, you know what, similar source. Sometimes some of the composition coming directly from motor vehicle or biomass burning. Potassium, we know, coming from biomass burning. Potassium, it will never come from conversion of motor vehicle, right? So this is the criteria how we explain. Now let's move on. Time is limiting our here. The emission source, by using chemometrics model that we have shown here, we can identify quantitatively. Those emission source we also can integrate with some statistical function, potential source contribution function, PSCF, and we can define the source region. For example, factor 5, you can see it is more influencing from the Sumatra region, right? And the sample we collected, the time we collected the sample, maybe Dr. Didin can also explain better that in Sumatra region, there is often biomass burning, forest fire, right? So it is like logical if we can have this kind of visualization, can help us to know the source region of our, the source region, how that is impacting on our pollutant. And at the same time, there is another statistical function called concentration weighted trajectory. This is a trajectory model, but that trajectory model we can make use many ways. If you look in our some published paper, recent published paper, we have made so many modification to the trajectory model and applied to our work. It is always, do you know what purpose? Purpose is we want to have better explanation of our result. Exactly same thing here, PM10 or PM2.5. The concentration, by using this model, CWT statistical function, we can explain concentration, how, from which direction is more influencing, right? At the same time, also particle number concentration, we can define from which direction more influencing, right? We have a latest paper by Rahim, our student. If you want, you can look into the paper to take a try to know more information how she has explained. And then in the last slide here, I want to introduce you health risks, right? We know now how we can quantify the emission source. And even our previous two presenters, they also introduce us the emission inventory, right, for many different sources, right? Now our second or third challenge is this emission source, how we can integrate to the risks estimation, human health risks. For example, here in our one paper, if you want to know more, I have given for you inserted the bibliography of our paper. Now, from this paper, we have identified number of source, road dust, motor vehicle, coal burning, right? And this source, how about their health impact? We also can estimate the health concern, the contribution made by this source for PM 2.5. You can see the composition coming from this source. We all need to determine concentration, how much concentration contributed by each of the source for each of the variable. There is some work, right? If you want to know, you are welcome to read some of our paper that may help you. It is all because here I want to give you a flow from the beginning, fundamental until like health risks, so that our younger participant here, it may help them for writing their thesis, because we can do experiment. It is always a challenge how we can explain our result, right? So this flow, I do believe that it will help you to write your thesis, report your paper, right? You can write a good manuscript. It may help you to go through all peer review process. So thank you so much. So this is all about in my discussion, presentation. So thank you so much for your patience. If you have any question, you can let me know. You can write in the chat box here, or you can pass it to Dr. Verma. So thank you so much.
Thank you, Dr. Khan, for your nice presentation. First of all, we would like to apologize for the poor slide resolution, because we cannot read whatever you were presenting. The slide resolution was quite poor. So, but that's a limitation of the online workshop. So there are something which beyond our control. So, but your presentation was very nice, but except some resolution of the slides. Thank you so much for your presentation, and your presentation was really having a lot of new informations and innovative ideas. Now we request the participants to write your questions on the chat, the Q&A box, and then Dr. Khan will try to answer. There's already a question. How do you calculate method detection limit for any species? Is it from the blank filter results, or that is average plus 3 standard deviation?
Yeah, I mean, there are many ways we can calculate method detection limit. You can make use blank filter paper, yeah, that is acceptable. Or you can also use simply just a reagent that can also help you to determine the method detection limit. And to calculate method detection limit, it is simple method. Yeah, you can use 3 times of standard deviation. There are also many other way you can calculate method detection limit, but this is the simplest way, 3 times of standard deviation. But number of sample, at least it should be more than 5.
If suppose the total variables is added like PM 2.5 mass, how do you calculate uncertainty file for this PM 2.5 mass?
Right. I mean, for PMF, I mean, it is always suggested that for PM 2.5 mass concentration, yes, we still can calculate uncertainty. There are some method. Some of the paper here we have inserted, and the reference bibliography has given. If you look through, there is some statistical calculation. Those statistical calculation can help you to estimate the uncertainty for PM 2.5 or other composition. And in those calculation method, you don't really need to determine method detection limit.
Okay. Any more questions from the participants? Okay. I think, okay, there is a question. I cannot read. Why is that? Can you hear? Chat one. Something happened. Okay.
Scroll down.
Maybe one question here that
Yeah.
3 times of standard deviation or average plus 3 times standard deviation. As I told you also earlier that there are many ways. I mean, yeah, the first, as you said that Dr. Saifi maybe 3 times of standard deviation. Yes, this is also correct way. You can calculate method detection limit for each of the variable. Yeah, on top of there are many other way. Either way should be okay. And each of the instrument, this is a question also, the instrument we use, every instrument also has a like detection limit, lowest detection limit, and instrument also provides some method to calculate method detection limit, lowest method detection limit. So there are many ways we can calculate method detection limit for the variables. Yes.
Sometimes there are zero contribution from some factors. Factor resulted by PMF. What does it happen?
I mean, from my experience, 0 is also a number, right? And this is also logical, 0. You can keep the 0 as it is because 0 is also a value or also a number. If it is negative some value, sometimes it's also happen to appear I mean, some negative value from even from PMF. What all you can do, you have to exclude the negative value, negative contribution for your variable or from your factors. It is because the negative value, it has no physical meanings. So this is as simple as to everybody that negative value, if we deal with the concentration data, it has no physical meanings.
Okay. Any more comments, question from participants? If not, then now we have come to the end of the presentations on the emission inventory development module. This is the end of today's session of the capacity building workshop on air quality management. Thank you, expert speakers, for your presentations, which were full of the new informations. I believe all participants will benefit from the knowledge you shared. We are really thankful for your contribution to the workshop. Thank you, participants, for joining today. Thank you for your interest and participation. Please join tomorrow at 1 p.m. Thailand Standard Time for the third session of the workshop on Module 3, that is air quality modeling. We will upload the PPTs of today's presentation on the workshop website. Please visit the workshop website for reading materials relevant to the presentations of today's module. Also, please provide your evaluation feedback for today's session and the yesterday's one. Remember, evaluation feedback is needed for awarding you the certificate of participation. You may submit the evaluation for whole workshop at the end of the workshop, but it would be great if you could provide feedbacks after each session. Otherwise, you will forget the contents of the presentation. Thank you again and have a nice evening and stay safe. See you tomorrow at 1 p.m. Bangkok Standard Time. Thank you so much.